Okay, so welcome everybody to the plant virtual tour. This is where I work, one of the places I work, the plant 3A treatment plant. This is of course a aerial view of the plant. Just to the bottom is the 5 freeway, and on the other side of the plant is actually where the railroad runs all the way. Same railway as the Surfliner runs on, the main train that goes from San Diego all the way up, I believe all the way to Monterey. Anyhow, it's a top view. To the left of this aerial view, bottom left is the digester. Bottom left is the storage tank for the reclaimed water, and all the way to the right are the two digesters. Just to the left of the two digesters are they're like white squares kind of, and those are our primary tanks. They're covered for reduced odor complaints, and then our aeration tanks are not. They're the tanks just almost dead center, the rectangular ones. And then just to the left, the circular tanks are where the settling tanks are, called the secondary clarifiers. So we'll go ahead and start our tour. All right, so to give you a little bit of perspective, I'm out on the street now, over by the freeway. There's that big storage tank that I referred to. And here is where the power comes in, the power poles. There is the olive green service transformer. This is the transformer for the facility. I believe it's a 12K down to 480 volt. Comes over to this service enclosure. From there, as you can see, it says SDG&E, but from this point on, it belongs to us, and it goes underground. And it goes into building 40, if you guys can see that. It goes in over to that building. So we'll go pick it up over there. So we're back at building 40. Over there was the distribution panel, the service pad. And here's where it actually comes up out of the ground. I'm in the maintenance shop actually, but this is the panel where the wires are coming in from the street. And here they use this instead of a conduit pipe, it's just in a duct, what they call like a big duct or enclosure. And so I really like the layout here. It comes in here and then it goes right above us. You can see this is where the power is basically coming into the plant at the ceiling of the maintenance shop, and then it pokes up to the switchgear, which is right above, and that's where we'll be going next. So now I am directly above the maintenance shop, and this is where the power comes in. This is our distribution switchgear that we covered in the beginning of the class. In the center is the main circuit breaker. This is where you can come if there's no power at the plant. And we talked a little bit about the voltage transformers, the PTs, and they're inside this panel, and they knock down that 480 volt to a much lower voltage. I believe it's 120. So it's safe to open this door. And you just got a couple little wires there. but it's actually measuring the voltage to this entire facility. And here is the current, measuring the current of the entire facility. So right now, we look good. We've got, like we said, about 400 and about 480 volts. I have a selector right here. So right now, I'm looking at 1,2 AB. So if we go to 2,3, we're looking at the voltage between B and C. And then 3 to 1, that is the voltage between C and A. So I usually just leave this in between the 1, 2, but you can measure voltage between all three phases, make sure that we got good voltage coming. And then right now at this particular moment, this facility is using about 500 amps. And that should be about the same on A, B, and C. Well, let's just check it out. So I got 500 amps on A phase. Moved up a little bit on B. Yeah, it's all, it looks good. The whole idea is that the load should be balanced across all three phases. So power looks good coming into the plant, and then from the main breaker, that powers the bus bar going across this switch here. Gotta back up a little bit so you can see the whole thing. And then each one of these draw out style circuit breakers also has an ammeter to let you know what that particular motor control center is using. So this one here happens to be, this one is the MCCB, that's going to the influent building. That goes to our administrative building. This here is MCCA. It's got a little bit of a load on it. So that's the controls, and then the actual circuit breakers are down here. And I'll back up a little bit. So that's the draw out circuit breaker. So that circuit breaker actually racks out of the panel completely, and we covered this a little bit. All the different settings that are available. We have the short delay, the long delay, and also the time settings as well. With these large breakers, when you have to recharge them, there's a handle here. You got to pump them up. You'll know when they're fully charged because the handle will get real easy to move, and then you operate this push to close button. That's how you operate these breakers. Okay. This facility has a power factor correction bank, which is right here in the center. We talked about that a little bit. And then we have some MCCs. This one is MCC-E. E is being fed by this draw-out breaker right here. And behind me is a relatively large one. This is MCC-D. MCC-D should have the most load right now. It drives our blowers. And here is D. And yeah, it's got a little bit of load on it. These are the smaller buckets. The buckets they're depending on the horsepower of the motor. You know, a smaller motor is going to have a smaller bucket. And you can see these ones are pretty big. These are the 250 horsepower blowers that we have here. And let's see if I can open up one of these for you. This one should be fine. Okay, this is a large starter for one of our blowers. It's offline right now. Not really sure, but one of our operations staff has this locked out. This is what they call it's a soft starter. It's a transformer start. So it has, as you notice, it has several different starters. It's got one here, and then these are just some very large contactors. Okay. Here's the transformer. So the way this thing works is when you go to start this motor, power is routed through this contactor right there, and through the transformer. So a lower voltage is applied to the motor by running it through this transformer, and that'll get it wound up, get it going. And then we have a timer right here that's gonna probably do that for about 8 seconds and give it a good jump, a good rotation. And then after it times out, that starter on the left is going to open, and the starter on the right is going to close, and it's just going to put full voltage to the motor. So that is a soft starter. Reduces the inrush current by initially starting the motor with a lower voltage that's supplied through a transformer. See, while I'm up here, here's our lighting panels. So throughout the plant, we have outlets, we have instrumentation, we have all kinds of things that don't require 480 volts. And so this is very similar to what you probably see at your house. These smaller circuit breakers, this is where they're going. These ones on the left here, CV is a control valve, so we have some motor operated valves that are 110 volt. Sprinklers, some lights, some receptacles, all kinds of stuff here. These EA actually supposed to be AE, and those are analytical. Those are powering some analytical instruments that we have here. Some pH meters and some stuff like that. Here's some more control valves. We got a sampler. Anyhow, we got a level sensor. But these are all loads that just only require 120 volts. And above are the transformers that are reducing the voltage from 480 down to 208, and then bringing the neutral down, and then any of the legs 208 to neutral is 120. They are being fed from probably this panel here. Yeah, so here is that's for one of them, and that's for the other. And that's the 480 volt circuit breaker for the primary side of these lighting transformers. And then on the secondary, these are the distribution panels for all of the single phase power around the plant.
here are some variable frequency drives. These are for our return activated sludge pumps, Allen Bradley. This is called the HIM. It's where we can get some information. I think I can get in here where you can see how many hertz this particular motor, what speed it's running at right now. Kind of hard to see. So it's up on the top bar. We actually have quite a few of them here. These are for our waste activated sludge pumps. So you can see there's quite a few of these VFDs, and this is only for the, this is just the ones for the aeration basin. A couple more, a little bit. I think these ones are 20 horse. These are offline right now because we're not making reclaimed water today, but that's the frequency command right there for these applied pumps. So this is kind of our main power distribution room right here. Is our dewatering building, and this is where our centrifuges are. What these do is they take our final solids out of our digesters, and they dewater them. They spin the water out, dispose of the what they call the cake, the solids, in some bins that are below us, and they haul it out of here. These are some pretty good size. This is a pretty good size machinery. This is the main drive motor here. I believe it's 125 horsepower. And then this is the scroll motor. This is basically the motor that ejects the cake out of the center of the centrifuge. This is our local HMI for controlling this machine. Here the operators are able to start, stop. They're able to monitor all the variables that are real time. They're able to go over to the polymer set points for the sludge and the polymer, the flow for the sludge, and how much their feed going to feed to the machine. The variable frequency drives are behind this panel, and here are the displays outside for it. Some alarms. This is a conveyor here. This conveyor is what takes the solids out of the machine and then moves it over to the unloading area, which you can kind of see beneath us. Okay, this is one of our process PLCs. This controls all of the equipment that we've covered so far: the RAS pumps, the blowers, applied pumps, centrifuges. So I'll stand back a little bit. And so this is the brains of the system, the communications, all of the control algorithms that we talked about, and we even built a couple of programs. This module on the left here is our PLC. It has an Ethernet connection that allows it to communicate with the main SCADA computers and also to communicate with other PLCs. They all kind of tie together and work together. For example, this PLC here gets a signal from that HMI we were looking at just before over the dewatering building, and then through the Ethernet connection goes to another PLC where the sludge dewatering pumps are actually located, and then from an analog output over at the other PLC it's actually commanding the sludge dewatering pumps depending on what the operator wants from here. But as you can see, there's several different links. Nothing here is really close together. Everything's kind of in a different building. Many parts of the plant are located in different areas. So we'll back up a little bit, and this is one rack. The PLC, the brains is on the left, and all this stuff here is input output. All of its input output going to turning stuff on and off, commanding stuff on and off, and looking at those things both in digital on-off values and also in analog values. And then over here it's the same thing. This is just an extended I/O rack. This cable right here, this remote I/O adapter, it simply goes over to the main and connects right here. And all it does, it just makes this first rack bigger, so to speak. Okay, so it's just extending and giving us all, significantly more I/O. This particular PLC cabinet has two extended I/O racks. There's one here, and there's one right below. So this one PLC has quite a bit of I/O, and then you can see all this mess down here. This is where all the wires coming from all the different equipments actually go into a terminal block and connecting to the I/O. Okay, so we just visited where the power comes into the plant. I thought what we do now is actually look at the plant as far as the process goes. So this building, we're gonna go to where the sewage comes into the plant, some of the machinery, that the bar screens, and then I think what I'll do is just basically follow the path of the water, and whatever looks interesting in terms of electrical instrumentation, we'll stop by and look at it. Okay. All right. So this is the influent building. This is where the sewage comes from underground to the plant. I guess we'll go in this door first. Oh, smells so lovely in here. Okay, not so much. Okay, so I think you guys can see those. That is that's a bar screen. So what this thing does is it gets all the big stuff out. Oh, cool, this one's running. So this claw here is going to go down and scoop all the poop and toilet paper and numerous other items that come through the sewer system that get stuck in a rake, stuck in a stream, and that's the rake that's going down. So you see there's quite a bit of control with this thing. Here's the auto switch, you can run it in hand, but on this one you can also run it in forward and reverse. Sometimes these things will get jammed up and you got to run it in reverse to unjam them. he's already hauling it back up. And you see here is the, hopefully there's enough light to see, but that's where the rake is, where it has all the sewage down there you can see coming into the plant. Here is a level sensor that's on the upstream of the bar rake, and another one right there on the downstream. And so it can tell when that screen starts to get clogged, because as it gets clogged, the upstream level is going to increase and the downstream level is going to decrease, and then it gets to a certain point where the differential level, kicks the machine on automatically. Not a whole lot else down here other than the two sensors for the level. This is where the sewage comes into the plant. And I'm getting out of here, it stinks. Okay, so we went in this door, and that is where the bar screens are, where the sewage arrives at the plant. Now we'll go in this door. This is where it goes to our influent wet well once all the big stuff has been taken out, after it's gone through the screen. This is our other motor control center being powered from where we were earlier, and this is MCCA. So we got quite a bit of business going on here. We got over here is where we have a lot of our ORT. ORT stands for odor reduction tower. We got circulation pumps, an ORT supply fan. There's also this is where all the grit pumps are, the controls. This is where the PLC is for this side of the plant, for the influent pump station. This PLC controls the bar screens, or actually monitors them. They have their own controllers. Same thing, basically. The PLC is located in this rack. I/O, more remote I/O, field wiring, and then over here, some more I/O. So we'll continue over to our influent pump station. And these are the variable frequency drives for our RSP, raw sewage pumps. These are the pumps that pump the raw sewage into our plant after it goes through the bar screen. Here are the control panels for the bar screens. We were looking at these earlier. Those level sensors are going to these ultrasonic level controllers right here. And you can see one is the upstream, 2 is the downstream, and 3 is the differential level. So this one is not going to run for a little while because you can see there's not a whole lot of differential level. This one here, yeah, these things are taking it easy right now. So here is our raw sewage pump VFDs, and then this is motor control center B. So these relatively larger variable frequency drives. You can see that the number 2 pump is running right now. And here's where those pumps are actually located. We're going to come back here in a second because this is critical piece of equipment. While we go look at the raw sewage pumps, try to guess what that's for. By the way, this is my storage area. Yes, it's a mess. A little better look at the raw sewage pumps. This is pretty typical of what a lift station would look like also. The sewage comes into the plant, as you can see, about a good, at least 60, 70 feet below grade into the wet well. And below us, of course, is the wet well, and it's, oh, excuse me, no, the wet well is actually on the other side of that wall. You see where the inlet pipes are. Okay, so any four of those pumps all pump to that one large common manifold, and then we'll go back over there and we'll look at the influent flow meter. Okay. So again, here's that manifold, and this is our mag meter. This is a 24-inch mag meter made by Rosemount. Currently, there are about 1,500 gallons per minute coming to the plant. And these pumps will slow down and speed up according to how much level is in the wet well. All they do is maintain a wet well. Okay. So the sewage comes over to the plant at this location, and it comes out of this building right over into here, and these covered tanks is our grit chamber. And so a lot of the heavy stuff, the sand, gravel, I don't know, seeds. You folks that work at the wastewater plants know better than I do, but stuff that sinks pretty quick falls down into this tank that runs across here as we begin the trek of the sewage through what we call the primary tanks. So the heavy stuff falls here. Now, once that's been removed, it comes down this center channel here, and then is distributed across all four. We have four primary sedimentation tanks. What you see here is part of the odor control system. All these are covered, and then we suck all the sewer fumes through this inline fan right here, and it goes to our odor scrubber. These are the drives that drive the chains and the flights that take all of the stuff that settles in the primary tanks and scoots it over into a sump, into a low point at the bottom of the tank. So all the stuff that settles at the bottom gets scooped over into a sump, and all the stuff on the top gets scooted over to another channel that's over here. And that's what this channel does here. And these motors come on periodically, and what they do is they take all the stuff that's accumulated on this primary scum channel, all the light stuff that went to the top, and it scoots it over this direction, all the way over to here, and it ends up in this lovely tank right here. And there it is. They pump this out once a day. It doesn't collect too much. And there's the primary scum pump down there. That pump will come on when that level. This has a level control. When the level gets high, that pump comes on down below. And it, like everything else, all the solids get pumped over to the digesters. Now the stuff that went to the bottom, they go to the primary sludge pumps, not to be mistaken or confused with the primary scum. Scum is the stuff that goes up to the top. So of course all that's going to be down low because it's at the bottom of the tank. And this is our primary sludge pump gallery. That's our primary sludge flow meter, another mag meter. These are the grit pumps that I was talking about earlier. It takes all the heavy stuff and it just sends it back to the dewatering building where it kind of gets dewatered over there too. They call it a grit classifier. And the grit classifier, again, it takes all the little rocks and the seeds and the heavy stuff and it just puts it into a bin. These are the primary sludge pumps here. On the other side of this wall is that sump I was talking about where all the heavy stuff falls to. And these are the pumps that come on periodically to take all that sludge, that thick stuff that's settled to the bottom of the tank, and of course sends it over to the digester. These are typical, this particular machine. This is called a grinder. It takes the primary sludge and it sends it through this grinder before it sends it through the pump. It's better for the pump to if something, you know, gets through that's kind of large and not good for the pump, then this grinder will chop it up first. Okay, so I just gave it another quick. We're over by the railroad tracks now. Okay, I'll do a quick panorama. There's the influent building there. Behind it is the digesters. This building here is the dewatering building, the power building, the maintenance shop, and the blowers are over in this building as well. Let's do this. Let's, before I start taking you to the next path of the water, these are the primary tanks here and they go over to the aeration basins. Let's do this. Let's do a 180 and let's do a quick tour of where all the solids go. The primary sludge, the scum, all the solids that get collected and pumped go to the digester. So a couple things over here. These are our dissolved air flotation thickeners. Call them a DAF. Some of the sludge that gets pumped over here, it's got too much water in it, and it has so much water that we don't want to put such a high concentration of water into our digesters. What we really want in the digesters is some very viscous, thick sludge. Okay, we don't want to put too much water in there. It has a negative effect. There's 2 digesters. This is the heat exchanger that keeps the digesters nice and warm. We try to keep the temperatures inside the digesters a very comfortable, biologically ideal temperature, so it'll promote quick decay of all the organic stuff that's inside the tanks. These DAFs, what they do is they take our waste activated sludge and they thicken it, and once they're done thickening it, they put the thickened material into the digesters, and of course the water goes back to the plant. On our left here, these are our polymer tanks that we use for coagulant to assist in the dewatering process. Okay, back on track here. So these are the primary sedimentation tanks, and then we're going to go to the kind of the core of the process, which is the aeration. And that's where we put the bacteria to work. So in order to infuse all this air into the aeration tank, it takes quite a bit of power, and that's really the biggest energy consumer at this plant is the blowers. And we're going to go into the blower room real quickly. It's loud in there, so I'll just kind of show them to you. What we were looking at back there was a blower and also a motor operated valve. And here at this plant, that motor operated valve is what throttles air to the blower. That particular design, if the valve is closed, then the blower basically just sits there kind of like a neutral. It just coasts, and there's no load. It doesn't hurt it. And then as more air is needed, then that valve will open. And the only thing that valve does here at this particular facility is it maintains about 10 psi on this manifold system here, and that gives us all the air that we need to inject into the tanks. So coming from the blowers, it comes out this manifold here, and you can see it heads over to the other side for the other set of tanks, and over to this tank here. And then we have 2 aeration tanks. This is where the sewage comes in. It is consumed by all the bacteria that love this oxygen-rich environment. And they call this the Pass A. And it crosses here into the other tank, and they call this Pass B, okay? And in these 2 tanks, they can control the amount of dissolved oxygen, so it's ideal. They want to have just the right amount of oxygen too much is not good and not enough is not good, and that's about all I really know about that. It gets kind of complicated, and that's more of the operator expertise, but controlling the amount of air is a closed loop control. This is the motorized valve that will open and close depending on how much dissolved oxygen is in the tank and what the set point is from the operator, okay? So the sensor is right here. Here's the sensor for this tank. The sensor itself is underneath the orange ball, and the transmitter is right here, transmitter or controller. And so right now, in this on this tank, we've got 1.62 milligrams per liter in, I believe that's the pass B, and I think if we go up, yeah, pass A. Yeah, pass A has got, that's the pass that's right here. It's got 1.63. And then pass B, that's the one that's the furthest one, has got 1.8. And you'll see it'll make more sense when we look at the SCADA control screen. With the operators, they can put in a set point of how much dissolved oxygen they want these tanks to always have. That will measure the result compared to the set point and operate those control valves. So that was the aeration tanks. Okay, so as you can see with the aeration tanks, the sewage is stirred up all the time. The air keeps all of the solids, the bacteria and the sewage. By the time it comes out of the aeration tank, it really isn't sewage anymore. It's more just bacteria, because the sewage has all been eaten by the bacteria. And then it comes over here to what we call the secondary clarifiers. Back up a little bit so you can see it. Now this is going to do the same thing that it did in the primary tanks. All we're doing here is just letting this stuff settle out, okay? And what's going to happen over here, basically, in layman's terms, all the dead bacteria is going to go to the bottom, and there goes the train. All the dead bacteria is going to go to the bottom, and some pretty clear, good-looking water is coming out of the top. So this is what they call secondary effluent. It is water. It's got a little bit of turbidity to it, not near as much as the sewage, of course. But of course, you know, it still hasn't been disinfected and it hasn't been filtered. So in order to discharge it here as reclaimed water, as usable reclaimed water, it has to go what we call here the AWT, and that stands for Advanced Water Treatment. Just to finish up here on the secondary clarifiers, just like the primary clarifiers, this stuff, the sludge settles to the bottom of this tank. And I think you'll be able to get a better look at one of these tanks look like empty in a minute here. So I'm gonna take you to one that's empty. But a majority of that sludge that settles to the bottom gets pumped back over to the aeration basin. And that's what keeps the population of the bacteria, the numbers good, the ratio. So a certain percentage of this, of the bacteria that settle to the bottom of this secondary clarifier goes back, and they call that return activated sludge. These are the RAS, or return activated sludge pumps right here. The variable frequency drives are going to automatically return the correct percentage of activated sludge proportional to the amount of flow that comes to the plant. So the more flow that's coming through this plant, then the more of this sludge we got to return and keep the bugs going here. Okay. So there's quite a bit of closed loop control here. This is the mag meter for the return activated sludge. And so this is where we get our process variable. On SCADA, we will put the percentage of how much we want to return of plant flow. Okay. Say if, I think, we'll see when we go in. I think they usually return about 20 to 30% of what the plant flow is. Okay. And then some of this stuff has got to be wasted. Okay. This plant is a lot like us, like a mammal, and so we have to waste some of this stuff out of here. Okay. And the wasting, the WAS, like I mentioned before, it has to be thickened. It has a little bit too much water in it, and it goes over to the DAF, okay, where it gets thickened, and it goes to the digester. And so the wasting pumps are down there, but that's what they do. Okay. Here's what one of these tanks looks like empty. And beneath me is what they call the RAS channel. That's where the water goes back to the aeration basin, where it's pumped here from the RAS pumps. And right now we have two secondary clarifiers that are online, and here's the other one where we're actually treating water. Okay, so that's pretty much kind of the end of the road when it comes to reclaiming the water from the sewage. But we still got some more tour left. I'm going to show you the advanced water treatment where we disinfect and we filter. But before I do that, I want to show you this. We mentioned our digesters. Our digesters collect all of the solids from the plant, and we want to break them down, decompose them, and the byproduct of that is methane gas. Okay, and so all wastewater treatment plants have one of these, and this is called a flare. And the flare is a pretty simple machine. It's gonna simply take that waste gas, and as the pressure builds up inside the digester, when it gets too high, it's gonna open some valves. It's got a flame, a pilot light starter, and it's simply gonna burn off that waste gas. The gas is usable, and so a lot of plants have various reuse programs where they'll take that methane gas and they'll run some cogeneration, some electrical generators. I've worked at plants where they take the methane gas and they use the gas to drive gas-powered engines, to drive directly to the blowers. And so when you have those types of reuse programs, these plants can almost be completely self-sufficient in terms of energy. So it's pretty cool. And it's running right now. You can kind of hear it. Well, actually you can see it. We look through here. There it is. These louvers here, what they do is AQMD wants us to maintain at least 1,400 degrees burn temperature in this flare, and what we do is we close. If you close the louvers, then it increases the temperature inside the flare, the actual burn off temperature. If you open the louvers, then it introduces more air and it cools it down, and that's how we maintain again, closed loop control. The control variable here is the louvers. That's what we're controlling. Here is the little MOV. It's a motor operated actuator. You see it's connected to these linkages here. Stand back a little bit. Again, closed loop control. Now this is a, we talked about this a little bit in the class. This is a standalone closed loop PID controller. This one doesn't have a PLC. And you can see that there's a set point of 1450. This thing's doing a pretty damn good job. It's maintaining it right there on the set point. So process variable is these thermocouples that are going up the stack here. There's 3 of them, and the operator can select which one of them it's actually going to use. The reason there's 3 is because if we're burning off a lot of gas, then we have to use the thermocouples that are a little bit higher on the stack, because the flame goes up higher. But the process variable is the temperature of the flare measured by the thermocouple. The set point is right here, determined by the operator, who puts it into right there on the right, top right, says set point select, and he enters a set point. He or she enters a set point right there. And then the control variable again is this actuator right here that's operating these louvers, and that's how we maintain 1450 degrees according to what air quality. Here's the permit for it from South Coast Air Quality Management. So that's how we stay compliant. Okay, well, I'm gonna start walking back over to the AWT. Okay, I hope we've gotten everything up to this point. Now, this is again our secondary clarifiers, and this is where we are going to clean up the water, polish it, and make it official reclaimed water. Okay, so the first thing that happens is the water, the good water that comes out of the top of these, that decants off the top of these secondary clarifiers, goes in to this wet well, which is beneath my feet, and here's the opening to it. Okay, and they call this the here they call this the applied wet well. And so we got a couple things going on here. This is a good location for these pumps. These are they call these the 3W pumps. And what they do is they take that clean water and they pump it through a system throughout the plant that we can use to hose things off with. We use it for seal water, for our pumps. There's a whole list. They use it for the dewatering, to mix the polymer. There's a lot of what they call utility water use, where we need water, internally at the plant, for a variety of different purposes. And so that's what these pumps here do. And then over here is where the actual applied pumps are, and these pumps are going to pump water into this thing here, which is the filters. And it's really too bad we couldn't all get together for a plant tour. That would have been fun. Make it a pizza night too. Okay, so we're not running right now. There's just not a demand for the reclaimed water, but this is a filter. And down there is the filter bed. They use, I believe it's a number 20 grit sand here. So I wish these were running, but they're not. You can see where the water typically comes up. The water actually it actually fills up here first, and this is where they mix it with some polymer to get some flocculation go, get all the solids to kind of clump together to flock, and then from there it goes into the filters. We have 4 chambers. Chamber 2, chamber 3, and chamber 4. So the way these filters work is the water comes up and you can see about where the normal level is. You can see, it's kind of interesting, these black things down here are level sensors that we have them in there, but they're actually not being used for anything. We found them to be quite unreliable, and so we ended up putting an ultrasonic level sensor, which works great. And the nice thing about the ultrasonic level sensor is that we can change the backwash levels, the fill level, whatever levels we want to ride. There's another level called the air scour level. That's when it's backwashing, how much water we want to be inside the tank when we do the air scour. And so this ultrasonic level controller does a much better job. This is the control panel, and I wanted to point out these. This valve here is the fill valve. This is where the water comes from this center channel and goes into the filter. It is pneumatically controlled. That's the pneumatic actuator there. You have the 2 air lines. The 2 air lines are going up into here, and then up inside the panel we have a couple of pneumatic solenoids that open and close with that air directional valve. We give it 120 volts and it shifts the spool over, directs air to the different sides of this pneumatic actuator, and opens and closes that feed valve. On this filter system, all the valves, none of them are modulating. They're all open and close. So it's a good application for pneumatics. But anyhow, that's what they put on it. So that's the top side of the filters. Level sensor. Our filters have an HMI, so you can kind of take a look at the system, see what's going on. Make it a little better. Here's the air compressor that gives us our service air to operate those pneumatically operated valves. And then these are the valves for the backwash. So looking at the side of the filter tank here, this pipe right here, and it's marked a mud well, when we go into backwash, because what's going to happen is the water is going to go through this filter. All of the dirt, you know, and the solids are going to get captured in the sand. And of course, eventually the sand is going to be plugged. And as it gets plugged, the water level in the tank is going to slowly start to creep up higher and higher because it's not getting through the sand bed quick enough. So once it gets up to that set point, that we tell it, the level's high, it's time to backwash, it kicks in a sequence. The first thing that happens is the inlet valve that was up top closes, so we don't feed it anymore, okay? And then this mud well valve, the inlet valve closes up top. This mud well valve is going to open, it's going to drain down the tank, and we'll drain it down about 3/4 of the way, okay? Then what we're going to do is this backwash valve, this valve is going to open. This filtered valve, that's the water that's coming out, it's going to close, and we're going to reverse the flow through the sand and push all that crap up out of the sand bed, and it's going to be pushed up and out, and then come out of this and go into what we call the mud well, okay? And they'll do that for about 5 minutes or so. Also, while that's occurring, they do what's called an air scour, where they have a pipe at the very bottom of the tank, and we just blow a bunch of air into it. It just kind of agitates it and mixes it all up, and it helps get all that stuff out of the sand, okay? So that's a backwash. And that's how these things maintain, and they just kind of cycle automatically throughout the day and the night when they're online, okay? So the clean water, when it's filtered, it's open, comes out here. When we backwash, we close this valve, we open the backwash, we send the water the opposite direction into the tank, reverse it through the sand, and then all the dirt gets purged out of the sand and comes out of this pipe here, and that goes to our mud well. The mud well has pumps. We simply push that back to the front end of the plant. And then here is the backwash line, and over there are the backwash pumps when it's time to backwash. So you can see quite a bit of instrumentation. Here's another mag meter where we're accounting for how much backwash we use, how much backwash water. Here is the clean water that actually leaves the plant, or excuse me, leaves the filter anyhow. And there is a mag meter for it. Okay, so at this point, the water, the secondary effluent has been filtered. It comes out at this filter effluent line here, and this thing right here that says Chem Engineer, that is where we dose it with bleach. Okay, we use bleach to disinfect in this plant. So Clean water comes out of the filters. It goes down into this wet well that's underground here. These pumps pull that clean water out, send it through this pipe right here. Bleach is added, okay? And the bleach is added proportionally to the amount of flow that that flow meter over there sees. And that's all controlled in the PLC. And that is going to be actually an open loop control. With that control, what we do is we just take a look at how much water is coming through the pipe, and we proportionally add enough bleach to get the chlorine residual that we want. And it's an open loop control because we're not looking at the chlorine residual meter. It's just too much, it takes too much time for it to react, and it's just not a feasible way of doing it. But what we do have on our open loop controls, we have a gain adjustment on the SCADA screen where they can look at the residual and say, you know what, man, the chlorine demand is kind of high. We're going to dose it a little bit harder, give a little bit chlorine proportionally to how much flow is coming through. And so the water is receives the bleach here, goes into the ground, and at that point it actually goes across the street. And I don't know if you can see that very well, but across the street there's that storage tank, and that's where the contact chamber is actually inside that tank, which is kind of interesting. So that's about it, except for SCADA. We'll take a look at the SCADA. We'll go in the office here in a second. I wanted to just take a quick little tour here of our bleach pumps. These are chemical dosing pumps. These are our chemical dosing pumps. You notice the tube that is used for calibration purposes to calibrate the pumps, make sure they're dosing what they say they're dosing. We have a couple other chlorine pumps here. These pumps here are for light dosing to the RAS. They have filaments here, and that's kind of an operator thing. Filaments are a bad type of microorganism, and they mess the plant up, and we try to kill them by putting a light dose of chlorine in the return activated sludge line as it goes back to the aeration basin. So that's what those are doing right now. Again, we're not making reclaimed water right now, so these bleach pumps are not running, but that's where they are. If they were running, you'd see the peristaltic pump spinning in the center. So with that, we'll walk over to the office and we'll take a look at the SCADA. Folks, we're now in the office, and this is where our SCADA computers are. Do a little 360 here. Got a little lab back here. And this is where all the operators hang out. And this is this is the SCADA computer right here, okay? So, there we go, that's better. This is the main overview screen, okay? And it kind of goes with the flow. You can see I've got a box here where I've done I got a quick glance look at the last 24 hours and how much flow has come to the plant. So that's 1.631 MGD. Then we can go to the headworks, and we can kind of back off a little bit here, and we can see what's going on at the where the sewage is coming into the plant. We've got our current flow coming into the plant. We got the levels for the two bar screens that we looked at earlier, upstream and downstream, and the differential. We've got our grit pumps, all in kind of a nice graphical format. And here's our influent wet well, okay? Shows you the level in the wet well. And right now the number 3 influent pump or raw sewage pump is running. And currently there's 1,485 gallons per minute coming to the plant, okay? If we click this, it'll take us to the next part of the plan. This is the grit pumps. Go back to here, the headworks. I just want to show you something I put in here recently. If I put a thing in here, the operators can put this, adjust this set point here, but if for some reason we ever see a flow that's right now above 3,000, and I can make this we can make it 2,500 or 3,000, whatever they want. If the flow goes higher than that set point, then we'll get an alarm, and we use that for well, the biggest thing is we have another agency that sometimes, without letting us know, will send us a lot of flow, and that's not a good thing if we're not really prepared for it. This particular plant, the way it's set up is the flow is actually dependent on what it gets divided upstream from us. There's primary tanks. So you get the idea. All the things that we were looking at earlier are kind of consolidated into a central location where the operation staff can, very easily manage it. Okay. Here's our digesters. Aeration tanks. We talked a little bit about the DO, dissolved oxygen, and that's the current level right now that's in the tank. And the control valves, it shows the percentage of how open they are. And here is the control page that allows the operation staff to put in whatever set point it is that they want to operate these tanks at. And it shows you these bars here, the green and the yellow, are indicating just how well the system is doing in terms of the set point and the process variable. Ideally, the green bar should be pretty close to the yellow. That's the set point, and then the green is the actual amount of dissolved oxygen. So right now you can see that this tank, the operators in here have a set point of 1.6, and the DO is 1.44. So it's probably trying to catch up a little bit. We're probably starting to take a little more flow into the plant. BPAS is doing real well. The set point is 1.10, and the PV is 1.15, so that's pretty close. I'm not even sure if they're even running flow through our other tanks right now. I put these in recently here. This allows us to give us some deadband between 0 and 1 part. There's no sense in having our actuators opening and closing all the time. If 0.1 ppm is good enough in terms of plus or minus, for the DO, then this deadband will say, okay, well, if you're within 0.1 ppm, then we'll just leave you alone. If you get higher, plus or minus 0.1, then it's going to go ahead and operate the valve and try and correct it. And then we also have these low clamps. I've got a low control variable clamp that says never close the valve completely, even at low flow. Even if the DO starts to spike up when we have low flow, they can set that here. They can say that never close it more than 5%. So it'll always be at least 5% open. So this is our SCADA screens, and you have two of them here so that two people can work. Oh, the trending. I should probably. You can go to any of these flow meters here. Let's find one that's got a lot of flow going through it. Well, let's take a look at the level. If you double click the level, it gives you a nice trend, and it'll tell you what the level's been over the last 24 hours. That's what the level has been in the influent wet well. Here's the influent flow. We'll double click it. You can see there's, you know, the flow coming to the plant, as you can see, is very diurnal. Looks like about 9 o'clock at night is when we see our high flow here. These spikes that you see, where it's going up and down, that's just when the pumps swap duty. They go off on and off briefly. That's all that is. And you can see, looks like about 3-4 o'clock in the morning, we got very little flow coming to the plant, and everybody wakes up in the morning and look at all the sewage coming to us. So again, that's just a graphical illustration of what's happening to the plant. But like I told you before, the real nuts and bolts is really in the PLC and the PLC programming. So over here in my office, I'll just kind of bring that up real quick. And here is the PLC for the filter side, the clean side. This is where the secondary clarifiers are, the filters, the disinfection, and a lot of other stuff. Aeration, I think, is over here too. Not quite as much I/O. There's the PLC there, and it's a host rack, and then a little bit of I/O in this remote rack there. So this is where I do all the PLC programming. This is what the software looks like for Allen-Bradley. And this particular program here is for PLC-B. That was the larger one that we looked at earlier in the tour, at the very beginning of the tour. We were back in the where the blowers were, and the blower starters and the power distribution. And you can see there's quite a few processes that are in this PLC. We're controlling aeration, the RAS-WAS, the air compressor system, the scum pump, the applied pumps, the odor reduction towers, the boilers, the centrifuges, dewatering, and of course we have some logic that we have to perform for the alarm system here. And you'll see some things that probably look a little bit familiar, perhaps. We're doing some computing here. We're taking some values, and here we're scaling a value here, so it means something to us, like we did in our exercise we did the other day. Taking the aeration blower low pressure alarm set point, and we're scaling it. Some timers here. We're saying, hey, if the pressure drops below a certain amount, then we're gonna have an alarm that says, hey, one of the blowers went off because we don't have any pressure in the manifold. And so it just goes on and on and on. All the different functions, all the different algorithms that are required to automate this plant all live in this PLC.
just to give you an idea how much programming is in here. All of this is just for the aeration control of the maintaining the correct amount of DO, controlling the valves, operating the blowers, calling for the blowers if one of them fails, the sequences fail, or the many different types of failures that can occur, whether it be in the motor. For example, here we got for number 3, high winding temp, high bearing temp, fail to run, swapping them from lead to lag. And this is the algorithms that automatically control the valves to maintain that DO that we were talking about. Anyhow, quite a bit of stuff here, so it keeps us busy. I hope you enjoyed the tour. Again, it's unfortunate that we couldn't all meet and do more of a hands-on thing, but I hope this was helpful to kind of give you an idea of what is here and what you can look forward to as you move on with your education and your career. All right, guys. Again, if you could go ahead and let's see here. If you could go ahead and go on to the discussion board, give me about 300 words minimum of whatever you found interesting about this place. What I'll leave it up to you. We're not looking for anything in particular. Okay. So give us, and then please go ahead and respond to a few of your classmates. Okay, and that'll be our last graded assignment. Y'all take care, and we'll talk soon. Okay.